2.6 Rational Functions and Asymptotes. A rational function can be written in the form f of x, n of x over d of x, where n of x and d of x are both polynomials, and d of x does not equal 0. In general, the domain of a rational function includes all real numbers except any x values that make the denominator 0. Find the domain of the function and discuss the behavior of f near any excluded values. So first, we need to go ahead and plot some points. We know the denominator cannot be 0, so we're not going to include 0 in our list of values, but we could include points like 1, 2, -1, -2, and even 1/2. So as we plug in each of these into the function, 1 over 1 would make 1, 1 over 2 would make 1/2, 1 over -1 would make -1, 1 over -2 would make -1/2, and when you plug in 1/2, 1 over 1/2, you multiply by the reciprocal, so you end up with 2. Go ahead and plot these points. And then you're going to go ahead and connect them with a nice smooth curve. Now, as we discussed, you're going to get closer and closer to 0, but it'll never equal 0 because there's no value you can plug in for x that would cause the function to become 0. So what we end up with is this rational function, which is actually the parent function. Because it gets closer and closer to the x-axis but doesn't actually touch, the x-axis is a horizontal asymptote. And the y-axis is a vertical asymptote, which we designate using dashed lines. The domain is going to be all real numbers except for values that make the denominator 0. So in this case, we can't have x equaling 0. So we're going to go from -infinity up to 0, but not including 0, and then from 0 up to positive infinity. We use the U symbol, which represents union, to unite these two separate statements. If we had wanted to include 0, we would have used a bracket instead of a parenthesis, but we don't want to include 0, so we're not going to use a bracket. This notation is called interval notation. What is the behavior of f near any excluded values? Well, the graph curves to the x and to the y-axis. We're going to go ahead and do that again on number 2. So we're going to make sure that we don't include any value that would make that 0. So we're not going to include 1, but we could include 0 and 2 and 3 and 4 and -1, -2, and -3. So as we plug each of those in, we'll get our y values. And then we're going to plot these points. All right, when we connect this, what we can see is it doesn't quite look like the parent function in that now the x and y axis do not appear to be the vertical and horizontal asymptotes. Instead, it appears that we're getting closer and closer to y equals 1 and x equals 1. So the asymptotes have shifted. This isn't the most precise drawing, but if it were, you would be able to see that really, really clearly. So the domain is going to be all real numbers except the x value that would make the denominator 0, which is 1. So we're going to go from negative infinity up to 1, and then from 1 up to positive infinity. What are the behaviors of f near any excluded value? It curves to the line x equals 1 and y equals 1. So in conclusion, we have vertical and horizontal asymptotes. Recall from algebra, asymptotes are lines which the graph approaches but doesn't usually cross. What are the horizontal and vertical asymptotes in problem 1 and 2? Well, in the first problem, we had x equals 0 and y equals 0, and in problem 2, we had x equals 1 and y equals 1. And then we have the formal definition here of a vertical and a horizontal asymptote, whereas the line x of a is a vertical asymptote of the graph when the function goes to positive or negative infinity as x gets closer to a from the right or from the left. The line y equals b is a horizontal asymptote of the graph when the function approaches b as x goes to positive or negative infinity. So graphing is one way to find asymptotes. Unfortunately, it's not super accurate if you're not being really precise with your drawing. So it's actually better to find asymptotes algebraically. So to find vertical asymptotes without the graph, you simply set the denominator equal to 0 and solve for x, because vertical asymptotes will appear anywhere that the denominator is going to equal 0. To find horizontal asymptotes, you actually have to look at the degree of the numerator and denominator, because the horizontal asymptote will change. So let's first explore what's going to happen if the degree of the numerator is less than the degree of the denominator. So we have an example here where we have x to the first over x squared. We can go ahead and plug in large values for x, so as x goes to infinity, to see what happens to the y values. So we can plug in values like 100 or 1,000 or 1,000,000 to see what happens. So if we plug in 1,000 to our function, we would get 102 over 10,007, which is a pretty small fraction. But if we plug in an even bigger number, we're going to end up with an even smaller fraction. So it's getting smaller and smaller until it eventually approaches 0. That's actually going to be even more evident on number 4. So we have x to the first in the denominator and x to the 0 in the numerator, which is why you don't see it, because x to the 0 power would make just 1. So when we go to plug in large values of x and y here, it becomes really clear what happens. If I plug in 100, I'm going to end up with 1 over 103, which is pretty small. But if I plug in 1,000, now I end up with 1 over 1,003. So this little plus 3 becomes pretty much like insignificant the bigger and bigger the values are. But the numerator is going to stay smaller than the denominator, and as the denominator gets bigger and bigger as x goes to infinity, you're going to get closer and closer to y equals 0. So anytime the numerator is 1 degree less than the denominator, you're always going to have the asymptote y equals 0. That's not going to be the case if the degree of the numerator equals the degree of the denominator. So here we have x to the first over x to the first. Let's look at what happens as we plug in larger and larger values of x. Okay, so first we would get that, and then we would get this is pretty close to 300 divided by 200 if you were to estimate. This is pretty close to 3,000 divided by 2,000. This little plus 3 and minus 1 are pretty insignificant when you get bigger and bigger and bigger numbers. So what this ends up being is y equals about 3 over 2, and it will get closer and closer to that as you plug in larger and larger values. So essentially, the degree of the numerator and the denominator, when they're the same, your asymptote is y equals the leading coefficient, or in this case, 3/2. So let's try that again on 6 and see what happens. So again, we can see that this is going to be y equals 2, which was essentially the leading coefficient because the degree of the numerator and denominator were equal. So the horizontal asymptote, when they're equal, will be the leading coefficient over the leading coefficient. Now, a couple things that we need to note. You have 3 cases for horizontal asymptotes. You have the numerators less than the denominator, you get y equals 0. You get if they're equal, y equals the leading coefficient over the leading coefficient. What about if the numerator is bigger than the denominator? Then you will have no horizontal asymptote. Also, you're only going to have vertical asymptotes at zeros of the denominator. So if your denominator ends up being something like x squared plus 4, well, there's no value that you can plug in for x that would make the denominator equal 0. So this would be an example of when you have no vertical asymptotes, or it does not exist. So that is also a possibility. You can have none for horizontal, and you can also have none for vertical. All right, so now we are going to find in the asymptotes and holes in the graph for rational functions. What's a hole? A hole occurs when you have canceled factors. So the rule is you must always simplify the function first before you find vertical and horizontal asymptotes or any zeros of the function. So to simplify, you have to factor and see if any of the factors cancel. So here we have the factor x plus 2 canceling, which means my new function is x minus 1 over x minus 3. We now find our vertical and horizontal asymptotes from this new function. If you try to find it from the original, you will get the wrong answer. So my vertical asymptote is where the denominator equals 0, so that's going to be x equals 3. You can also find it by setting this equal to 0 and solving for x. So you can see it's x equals 3. My horizontal asymptote is going to be 1 because the degree of the numerator and denominator match. So I'm going to get y equals 1. Now we also have a hole at the canceled factor. So we set x plus 2 equal to 0, and that means we have a hole at negative 2. All right, let's go ahead and repeat that on number 8. So we can see right away that we have a hole at x equals negative 5. And then we are going to end up with a vertical asymptote at x equals 0 and a vertical or a horizontal asymptote at y equals positive 1. Number 9, it says find the domain of the function and decide whether the function is continuous. So a function is going to be continuous if you don't have any holes and you don't have any vertical asymptotes. So you always want to start by trying to factor, but unfortunately this one is not going to factor. You have to pay attention to this fact that there is no x term here, so it's not going to be factorable. So we're going to start by going ahead and setting the denominator equal to 0. So I'm going to get 2 equals x. So that's going to be my my vertical asymptote is going to be x equals 2. And then my horizontal asymptote is going to be y equals, these are both cubed, so it's going to be 3 over negative 2, so negative 3 over 2. And then is it continuous? No, it is not continuous because we have a vertical asymptote. And then finally we need to find the domain, and the domain is all real numbers except where you have vertical asymptotes, so except at 2. So we're going to get from negative infinity up to 2 to positive infinity. All right, so there are some functions that are a little tricky. So it says determine the domains of f and g, find any vertical asymptotes and holes in the graphs, explain how the two functions differ. So first of all, g of x is just a line. So the domain is just all real numbers. There's no asymptotes, there's no holes in a line. F of x, on the other hand, we need to simplify it first. And you can see here that we have a canceled factor, so f of x equals x minus 4. So it would appear that the domain of f of x is the same as g of x. It looks like they're the exact same function, but they are not, because f of x is going to have a hole at x equals negative 4. So essentially what this is going to look like is you're going to have a line like this, but at negative 4, there's going to be an open hole, as in that graph does not exist at negative 4. So that's how the two functions differ, is that one has the domain all real numbers, the other has the domain negative infinity up to negative 4, and then negative 4 to infinity. Number 11 is a little weird in that the wording of it is a bit strange. They want you to determine the value that f approaches as the magnitude of x increases. So they'll say, what happens to f of x when x is positive and large in magnitude? What happens when it is negative and large in magnitude? In other words, what happens when x goes to positive infinity, and what happens when x goes to negative infinity? That's all it's saying. So large in magnitude is just big in size. So they want you to plug in a big x value that is positive and a big x value that is negative, and then compare the two. So we're going to have 5 minus 1 over 100 and 5 minus negative 1 over 100. Now, just for the sake of this one problem, mixed numbers are fine, so we can just say this is going to be 4 and 99 over 100, whereas this is going to be 5 and 1 over 100. So comparing these two values, this one is slightly smaller than this one, which is slightly larger. So what happens to f of x when x is positive and large in magnitude? We get a slightly smaller value than when x is negative and large in magnitude. All right. Last two problems. Find the zeros of any of the rational function. So for number 12, zeros are always going to occur when y equals 0. So we plug in 0 for f of x. And this is going to become 0 equals x squared minus 9. Because if you multiply both sides by x plus 1, it's going to cancel here and just become 0 on the left side. So we're really just left with 0 equals x squared minus 9, which is going to be 9 equals x squared, or plus or minus 3 equals x. On number 13, you want to actually combine this into one fraction before you find the zeros. It's not totally necessary to do that for this problem, but it's going to be necessary in the future for similar problems. So we should just practice that skill right now. So I'm going to put 6 over 1, multiply the top and bottom by x minus 2 to get a common denominator. So I will get x minus 2 plus 4 all over the common denominator x minus 2. So I get 6x minus 12 plus 4 over x minus 2, which is 6x minus 8 over x minus 2. And then at this point, we set it equal to 0, and we'll get 0 equals 6x minus 8, or 8/6 equal x, which will be 4/3 equals x is our 0.